סימקים, אני חושב שזה פעם עידן. לא ידעתי שהוא בא, בכלל סימקים. אני חושב שזה עכשיו פה של קרמה. החליפו את השערת, ויש איזה שני וונדות כאילו, אחד רק אותם כבר, לא? זה שני ידי פלא והם עלפים. לא באתי איתם?
זה הרבה ילדי פלא,
לא, שניים ישראלים. לא, הודים. הם החליפו את ההשערה של זה שיש מערכות שטיינר עם מוטר.
יש מה?
מערכות שטיינר עם גרף גדול כרצון לך. אבל פתאום זה נפל על איזשהו פה בארץ, אני לא יודע, אולי נביא אותו מה? זה היה פתוח 50 שנה.
שמעתי גרף.
כן?
פה אני צריך מיקרופון או לא? עמרי, אתה יודע, פה אני צריך מיקרופון או לא?
אני כבר התחלתי לחשוב מבחינת כל ההרצאה.
כדאי, כי בעיקרון, זה מוקלט, יובל, אתה יודע, זה מוקלט
אני צריך את זה
אז כן, כן. וכולם דוברים עברית.
אבל אי אפשר כבר
באנגלית זה
משהו. בואו נתחיל את כולם. לא. אנגלית.
Okay, so let's start. We're very happy to have Shachar Lovett speak for the third and final lecture of the Erdős lecture series. So I guess most of you probably already either saw Shachar before, but I'm sure all of you have heard about him. So Shachar made many groundbreaking contributions in combinatorics, analysis, communication complexity, basically any field of complexity theory, and we're very happy to have him speak about geometry.
Geometry, okay. Thanks, Amri. Thank you for the kind introduction. Yeah, so this is going to be sort of a different talk to the previous ones. This is more geometric and trying to understand some specific questions. It's going to be a combinatorial question at the end, but it's going to be connected both to questions that come up in machine learning and questions that come up in discrete geometry. And you see it's a very clean, nice sort of a combinatorial question. And sort of, to me it was surprising, like people have asked this question for the last probably 40 years, and we still don't know how to solve it, but we can get closer to a solution. But I think it's a very nice, clean solution. It's a very nice, clean problem, and I'm hoping for a nice, clean solution. We don't have a clean solution, we have something, but maybe somebody else can come up with a clean solution. But let me start with sort of the problem. So it's called the point location problem, and there are two different equivalent formulations where these questions come up. מה לעשות? אתה תאורה? כן, אולי כדאי. Okay, is it this better? Okay, good. Oh, perfect. Yes. So if you came in, we just started, so you didn't miss anything. So this is like one formulation of the problem. So you're in RD, you're in sort of D-dimensional space, and you have a bunch of hyperplanes that you know. So these are not your input, this is what defines the problem. And then your input is just this one point here. And you don't know this point. And your goal is to try to figure out, in which cell in this configuration it belongs to. Like in this case, it belongs to this sort of, triangle here. So what does it? So and the point is that you don't really know this point. So you have sort of limited way of accessing this point. You have sort of queries. You ask queries about this point. And then what you want to figure out is that this point lies below this line and above this line on the left side of this line. Okay. So and the model, the computational model we're going to look at is called linear decision trees. And in this model, you don't have access to this input point, but you can ask linear questions. So you can sort of choose a line and say, are you on the left side or the right side, or maybe on top of it, and then you just keep going, and you want at the end to figure out where this point is. So for example, let's do the illustration. So you're here, you know nothing. So you ask about this line, are you above or below this line? Say, well, I'm below this line. So you're somewhere in this sort of half of plane. And then maybe you ask about this line, and now you say, well, I'm on the right. So now you're in this sort of cone, and you sort of keep going. And at the end, you know where you are. Okay? And so that's a question. How many questions should you ask?
What kind of access do you have to the lines?
Oh, the lines you know.
The lines are fixed, so you build an algorithm for a particular set.
Yes. So the lines are part of the problem. Yeah. Yes.
Can you ask for a new line that's not in your
Oh, that's a very good question. So one question is, what would be a good strategy? Should I just ask about these lines, or should I ask about other lines? That's a very. We'll see that soon. Okay, but that's a very good question, right? It seems. Yes.
To make sure if the hyperplanes are just, let's say, for a Noy diagram or something, this is exactly nearest neighbors.
Yes.
So this is the nearest neighbors.
It's a generalization of nearest neighbor search, but yeah. Here you say this specific case is going to be nearest neighbor. Okay. Actually, no, for nearest neighbor, yeah, okay. Yes. Okay, so that's one way to think about this problem. Here's another way that's sort of equivalent. So instead of asking these sort of linear queries, you can think about it as a linear decision tree. So it's a tree, it makes decisions. And every node you can ask a linear question about your point. Is it assume for simplicity all the hyperplanes go through 0, just to simplify our lives. So you can ask some linear question. You say the answer is either negative, 0, or positive, and you decide which way to go. Okay? Good. And again, the number of cores is just the depth of this tree. Okay, so let's try to define it a bit more formally. So I'll think about the hyperplanes. I'm assuming all my hyperplanes are homogeneous. They go through 0. So they're specified by the normal vector. So I have h1 up to hn, which are the normals to the hyperplanes. I know them. That's not my input. My input is this one point x. And my goal is to decide the cell of x. So what's a cell of x? So information theoretically, it means that for every hyperplane, I want to know if x is above it, below it, or on top of it. So if the inner product is positive, negative, or 0. So the sign of it. So I want to somehow compute this, at least implicitly this vector of sign. This determines the cell. And okay, what access do I have to the point? I have queries. So I can choose a hyperplane H, maybe one of the ones I got. That's natural, but maybe something else, right? Like you were asking, and I'll try to decide the sign. Is it positive, negative, or 0? Okay? So that's the full computational problem. You're given n hyperplanes. You're given a point. You want to figure out in which cell it sits, and you're allowed to ask questions about hyperplanes. Okay? And the main question that we'll try to understand is, how many queries do you need to do that? Like information theoretically, even. Of course, if you can do it information theoretically, you want to ask how to do it, computationally efficiently. But as you will see, even just a statistical question is hard. And then which queries, right? Like you were asking, just the ones that you got in H, just the ones that you actually care about, or should you ask about other hyperplanes that somehow come out of thin air? Yeah. Okay. Any questions about the problem? No? Okay, good.
Just a little comment.
Yes.
X is not really input. It's the subject of the question. Not really, you don't get to see.
It's like an oracle. You're an oracle to ask questions about X. So yeah. Yes, okay. So here, let's do some simple bounds. So the trivial bound is you don't do anything smart. You just ask all these n hyperplanes, and queries, you're done. Okay, that's simple. What's a lower bound? So I'm claiming that d log n is going to be a lower bound. What is d log n? D is a dimension, and well, log n is log the number of hyperplanes. And I'll show you the proof. It's just because this is just the total number of possible answers you could have. So why d log n is a lower bound? Because you say, well, if I choose like n generic hyperplanes, let's say, they partition space into regions. Like if I have actually the plane on the board, and I draw n lines, and ask how many polygons do you get, it won't be exponential in n, it's going to be n squared, right? And in general, in d dimensions, it's not going to be exponential in n. It's going to be n to the d. Okay? So since you have n to the d possible answers, and since every question returns one of 3 answers, you need a log of the number of answers to get the minimum number of questions, right? So this lower bound says nothing about what types of questions we're asking. This could be any type of question. So what we're trying to understand is that just by asking this type of linear questions, these very natural questions, is this enough to match this sort of information theoretic lower bound, or is there some gap there? Because we're only asking linear questions, you're losing something. Yes?
The fact that it's partitioned into n to the d cells, that's trivial, or you need to know something?
It's not hard.
No, precisely. It's sum of n choose j going from 0 to d.
Yeah.
And you prove it by induction.
Yes.
It's not a trivial thing, but it's like an exercise.
It's an exercise, yeah. If you want to see, for example, in the plane, so you'd say, let's say I already have a partition in the plane with n lines, and I have some number, I don't know, m cells. And you add one more line, so you can say, well, it crosses every line at most once, so it creates at most n new cells. So then you n, okay, good. You go plus n every time. Okay, good. And basically the same thing you do in higher dimensions. Okay, good. So now let me show you a different world where the same math question comes up, but in disguise, or not really in disguise, but sort of in equivalent form. So this is this world called active learning, and it starts with the following premise: that sort of if you want to do learning of data, some predictions, then what's easy to get today is like tons and tons of unlabeled data, right? You can download all the tweets and all the posts and all whatever, there are tons of them. But for many algorithms, what you really want is not unlabeled data, but labeled data. Like you want to say, to get like a news article and someone tell you, oh, this is about sports, or this is about, I don't know, politics or whatever, and then you can train your deep learning or whatever you want on this labeled data. And the problem is that, well, it's harder to get labeled data. And so what hopefully you want to do is say, well, I shouldn't be labeling everything. I should sort of smartly choose what objects I want to label, pay people to do them, and then use that in my learning algorithm that is supposed to get labeled data. So this area is called active learning, and it's not new. It started in the 90s. And really the whole question here is either practically or in theoretical models, asking how do I choose representative data points or unlabeled elements so that I can choose somebody to label them for me, and then I can hopefully use it to build like a good prediction. So how do we model it here? So we're going to look on a very sort of simple setting where we want to do active learning of half spaces. So what is active learning of half spaces? So I have data points, x in RD, that I want to label. And basically, what I don't know is a way of the labels, which is given by a hyperplane. So maybe I'll do a picture here. So it looks like that. So I have my points, the blue points. I know them. What I don't know is this red line, so crossing here. And I'm telling you that all the points above are going to be plus, and all the points below are going to be minus. And you want to figure out, which ones are plus, which ones are minus. And you want to do it by asking a few questions, right? So like, these are plus, these are minus, and okay, what questions can I ask? I can ask, for somebody to give me a label for a point. So I can ask somebody to maybe choose one of my points and give me the label. It's plus, it's above the line. Or maybe I can choose another point. It's not one of my data points, and ask somebody else to label this one. It's above the line. Okay. So again, it's a geometric question. But the whole point is the same question, right? The first question about about what's called a hyperplane arrangement, that's a question that people study a lot in discrete geometry. And this one, which we study in machine learning, are basically the same question. And just use sort of hyperplane point duality. It's all about, you have a bunch of things, and you're going to call them other hyperplanes or points, and you have another thing, and you care about the sign of the inner products. Okay. So we can use whichever framework we want. I have to tell you that a lot of the earlier work in this area, I'll tell you more about them, it was about people coming from the geometric community. So for them, it was more natural to use this sort of point location framework, and a lot of their algorithms and analysis came from a geometric type of analysis where you partition space and you do sort of various geometric things. But we're going to take this second approach, and somehow, because then it will be more natural to apply sort of machine learning techniques to this problem, and somehow it becomes sort of more easy to analyze. But they're equivalent. So you can choose whichever one you want. I'm going to choose the second one, the one of this active learning. So again, just to remind you, so this is going to be the question that we're going to study from now on. So it's going to be, I give you a bunch of points that you know. So you know the points. There is also a line that you don't know, or in general a hyperplane that you don't know. And you want to figure out that these are plus, and the other ones are minus. And you're allowed to ask questions about whatever point in space. And the question is, how many queries do you need to solve this problem? And can you match this sort of d log n normal? So let me show you two examples. One example where this problem is actually very easy. We're working in 1 dimensions. Okay, so already everything in 1 dimension everything should be easy, and it is easy. Okay, so let's see how does this look in 1 dimension. So I give you now points on a line, and remember, you know the points. What you don't know is this green line here, that is the threshold. And I tell you everything there's a threshold, such that everything above the threshold is labeled plus, and everything below the threshold is labeled minus. Right? But now I don't tell you the threshold, you just get these points. So what can you do? How can you solve this problem? Binary search, exactly, right? So that's okay. I don't know, first year, exercise. So you say, I'm going to do a binary search. So you start in the middle, you query a point, and you automatically knows everything to the right has to be a 1. You query another point, you know everything to the left has to be -1, and you keep going. Okay, great, binary search. So in 1 dimension, we can do binary search. We can label all the endpoints by just asking log n questions. What about 2 dimensions? Can you do binary search in 2 dimensions? Well, let's try. Let's see if you can do binary search in 2 dimensions. So what's the problem? It's very similar. I give you now a bunch of points in 2 dimensions, and I tell you, well, the ones, let's say, below the line are a +1, or the right are +1, to the left are -1, but you don't know the line, so all that you really get is the points. Can you solve this using binary search? So what do people here think? Can you do binary search in 2 dimensions? Suddenly it becomes less simple.
You can pre-process points, then range.
You know the points. You know everything. Right? You know the points. You know everything.
So range trees basically do it, like a 2-dimensional range tree, right?
No, because you're there for x is parallel, but they can diagonal, right? So so the first thing to try is to think about this type of data structures and say maybe first sort them on the x-axis and the y-axis, or this sort of. Okay, but the answer is that you can't. In general, if I only allow you to ask questions about the points themselves, there's nothing you can do. And here's here's a counterexample. I give you the points and they're on a circle. And I tell you, here's an extra promise. The line separates 1 point from the rest. So 1 point is labeled +1, all the rest are -1. So of course now you need to basically query all the points until you find this only +1 points. Okay? So this answers your question, right? If you just query the lines, or in the first version, only query the planes, you're going to get stuck very fast. Okay, so what can we do? Well, the obvious thing to do is to say, well, let's allow ourselves to also query other points. Like maybe I can query a point, here or here. And, can that help us? So the answer is yes. So for example, here, what you can show is that if you're allowed to query points outside the circle, then you can do it in a way we can recover log n. And what I want to show you is not this specific one for the plane. For the plane, we have like simple ways of doing that. But I want to show this general theory of what can do in general. Okay. And somehow, okay. So what's the general setup? So here's what we know, or what we knew before our work. So you have n points in Rd. The lower bound factor is d log n. So everything here is going to have this log n factor. So the interesting the evolution would be, how do the algorithms depend on the dimension d? And though this started being polynomial in d, even from the early 90s, and this work in 80s, it was like a special case that Erdős proved, and then Meiser realized he can generalize his algorithm to like a general set of points, and then.
His name is Meyer Alfred Heide.
Okay, good.
But even in his paper, he says that it's a general case.
I think it does, but then he only works out this case.
Yeah, I worked on this, but
Yes. Yeah,
that's
this
a
is-
complete problem.
yeah. Yeah, somehow along the development of the things, people have sort of invented all these sort of cool things, sort of discrete geometry, like, shattering and packing, and all this epsilon nets. And so a lot of good stuff came out of it.
No, it certainly didn't have D. It's polynomial.
What?
Neither of their Heidel had polynomial
In N. Yes. Because it was looking on like a knapsack. Like the whole point of this is to say, here's an NP-hard problem, but it has like a non-uniform algorithm running in polynomial time. That was like the main message here. But then people started caring about what should be the right dependence on D. And it seems that for like all this line of work up to Ezra Sharir, we're using sort of various types of geometric decomposition techniques. And these seem to get stuck at around D squared. And it wasn't, and it sort of, some point we were speculating that maybe things do get stuck at D squared because maybe there's sort of gap between what you can get from general queries versus linear queries. So one thing we showed is sort of not for the general case, but sort of assuming the points have some nice structure, they're not pathological, you can get ways of getting very, very close to the optimal bound, but under the assumption that the points are sort of not too crazy. But somehow it seems like the hard cases are always going to be the pathological cases in this case. So what can we do like in general without assuming anything? So this is what I want to tell you about today. Is this new work where what we can get is almost what we wanted to get. So what we wanted to get is something that looks like D log n. And what we got is that it almost looks like that. But for reasons that you're going to see later, we're going to pay some price at some point that we don't actually pay. And sort of one thing that comes up from this is sort of to get this type of like relatively tight bound, we need to not just try to understand things in general for points, but look at sort of the specific structure of the points that we get and build algorithms tailored for the specific structure that we get. So I want to tell you about that. And also I think there's an interesting open question at the end that people might like. I think it's clean. Okay. So yeah, so you'll see at the end, well, this algorithm really comes from two parts. One part gives you this, and that is more or less, relatively clean and nice. And this part gives you the suboptimal bound, and the algorithm is messy and not the right one, and should probably be improved. Okay. So now let me show you how do we do it. So again, here's going to be the setup. So you get this set of n points in d-dimensional space. You have this unknown hyperplane. Your goal is to learn the labels of all the points in X. And you have an oracle, and the oracle you can ask about the label of any point in R to the D with respect to this unknown hyperplane. So what can we do? So I'm going to use the following two notations for the talk. First of all, I can just, since I only care about things being positive or negative, it would be easier just to assume everything is normalized. So, all the points have, L to norm 1 and the hyperplane has L to norm 1, just so I don't have to keep carrying these constants here. It's just for convenience. And then I'm going to use...
Is this really without loss of generality?
Yes.
The hyperplanes go through the origin,
Because you just care about through the origin, just the inner product, if it's positive or negative.
No, that I understand. I wonder if the hyperplanes go through the origin, that's all you care about.
Yeah.
But is that not a loss of generality?
No, we can always, if it's non-homogeneous, you go to one dimension plus more, one more. Yeah. Yes, so it is without loss of generality. Okay, so I need two notations, the label and the margin. So the label is what we're going to care about. It says, take X, take H, compute the inner product, and tell me if it's positive or negative. Okay. The margin is going to be something we're going to use in the analysis or in the construction of the algorithm. It says, tell me what's the value of the absolute value, how close it is to 0 or 1. Okay, labels and margins. So in the general paradigm that we're going to do, it's going to be sort of a natural paradigm. I'm going to say, remember, my goal at the end is to make about D log n queries and label endpoints. And the algorithm is basically going to say, we're going to make about D queries, label half the points, and then keep going. Okay, so it's a very natural strategy. And I'm throughout the talk I'm going to hide polylog d factors. So everything will tell you approximately I'm going to lose some polylog d factors that we're not going to care about here. Okay, so how do we do it? So we're going to do it in steps. So step one is to say, well, let's say for now that my points are like random or generic, and what can we say about them? And say it's going to be easy to just label all the points that are far from this hyperplane. That's going to be a very, very simple, naive way of doing it. So first step is going to be, we can sort of say everything that's not too close to the hyperplane, all these parts, it's very, very easy to label. So let me show you that first. And then things become more interesting when you say, well, what is really close and what can we do then, and so on. So in particular, one thing that's true about random points, or I don't know, is that if you have a random, if h is a fixed unit vector and x is like a random unit vector, then the inner product is not too close to 0. It's a good probability. It's about 1 over root d. So let's just try to do that. Let's just start initially to label all the points that are slightly far, not too close to the hyperplane. I mean, again, the random is just sort of for intuition. We're not really be caring about random points, just sort of for intuition, why we should expect generic points to have large margin. So I'll show you that, how using about d queries we can label all these points. And that's going to be simple. So here's what we're going to show slightly more generally. Let's assume, I don't know, maybe half the points or some fraction of the points have margin at least epsilon, maybe 1 over poly d. Then I'm claiming we can just learn all of them with about d log d epsilon, about d queries. And so that's when at least, you see, if we choose epsilon to be like 1 over poly d, it's about d queries. So that, and again, that's just the first step. So let's do that. Let's start with something simple. So here's my hyperplane, here's my points. Let's assume I could just estimate every coordinate here, h1, h2, up to like a really tiny error. I'll show you in a second how to do that. And then I'm claiming then we can compute this in a product up to plus minus epsilon. So if if we know I get an answer that's more than epsilon, less than minus epsilon, I know that's a sign, that I can control the errors. So that's, again, nothing too deep going on here. So how do we do it? Again, it's also simple. So okay, let me just show it here. I'll explain. It's not super interesting, but also there's nothing too deep going on here. If I want to estimate, this hyperplane, all the coordinates of plus minus epsilon, I can look on each component. It's h input with ei, and then compute their signs, choose the maximum one, and then you use some linear queries to approximate all of them up to plus minus epsilon. Again, details are not super interesting, but all I want to say that you can approximate all the coordinates up to something that's more or less the right answer, plus minus epsilon, and that's enough. And that only helps me if I know x is far from the hyperplane, right? Because I added some errors, so everything that's far away, I'm never going to be too close. If I sort of, right, we take this hyperplane and we sort of estimated in sort of somewhat close to it. So if you're far, it doesn't matter. Of course, if you're close, it could mess up everything. So the interesting stuff is asking, what if there are no far points? What if all the points are like super close to the hyperplane, so that we cannot do this trick? So what can we do then? So again, ignore the details. Everything far, we can just label. Let's assume we just have low margin points. So this is where things will start to become interesting. Okay, so we dealt with the easy part. Let's move to the more interesting part. So how do we handle low margin points? So the next idea is to do something called vector scaling. So vector scaling is a way of taking points and applying a nonlinear transformation to them that preserves the labels, but might change their margin. Might move some points that are more close to be far from the hyperplane. So how do we do vector scaling? What is vector scaling? So again, do this. Okay. So here's the idea. So let's say A is some invertible, d by d matrix, some linear transformation. Think about the following operation. It's nonlinear. I apply A on X, I multiply them, and then I renormalize to get again a unit vector. Okay? So let me call this A acting on X, which again, this is not multiplying them because I'm always rescaling to get unit vectors. So why could this potentially be useful? Again, let's say A star is the conjugate. So the whole idea is to do this. Imagine we could replace my set of points X and my hyperplane H with a new set of points and a new hyperplane. my new set of points is going to be A applied to X. It's a new set of unit vectors. My new hyperplane is going to be A star applied to H. And then if you do the computation, you see that, well, the sign of the inner product stays the same, but the value changes in some weird way. So I'm not saying it always gets better, it just becomes different. So when things start moving around, you say, well, maybe there's a way of doing that and getting many points to be far from the hyperplane. Well, why not? We can hope. Okay, but again, we're doing this nonlinear transformation, and assuming we can, implement it. I mean, remember, we don't know H, so we're only sort of pretending that we have access to this A star H in our mind. But if you can work with that, at least we have hope of moving some point that are really close to becoming far away from the hyperplane. Okay, so here's a theorem. It says, if you have a set of points x in Rd, which is not degenerate, I'll define what it is in a second, then you can find this linear transformation that applying to x moves you to essentially being in an isotropic position. So let me just open stuff here. Okay, so first of all, we were not the first one to show it. It just there was a line of works where people showed this type of results, starting from Barthe and then Forster, and actually Forster's result is weaker than Barthe's result, but they were unaware of each other. And then there were improvements, and those the changes in these works is what is non-degenerate means. So we were able to get sort of the optimal non-degenerate condition. I mean, so when can you, okay, what is isotropic? Isotropic means that these points look the same in every direction. If you take this set of points and you look at the covariance matrix, it's a scale of identity. So if you project them to any direction, they have the same projection on average. Or formally, it's you can write it like that. Set of points y is an isotropic position. If for any unit norm v, you compute the L2 squared and you normalize, you get exactly 1/d in all the directions. So in all directions, they look the same. So when is it impossible to do it? Let's say all my points live in a low-dimensional space. Then of course I cannot change bases and get it to be in high-dimensional space. But also if you have too large of a fraction of my points living in a low-dimensional space, that would still be impossible. And if you do the calculations, like one case where that's going to fail is that if I have a k-dimensional space V that contains more than k over d fraction of my points. If that happens, nothing I'm going to do, changing their bases, whatever, can never move this set of points to be in a higher dimension. But once this condition is satisfied for the subspaces, then you can show that you can move this to be as close as you want to this isotropic position. And again, there were all these works that have proved this is true under slightly stronger assumptions. Okay, so we can apply this vector scaling, because if my set of points is degenerate, then it's very easy to do induction. You take this set of points in low dimension, you solve them, you go to the rest. So let me not go through that. So the interesting case is the set of points is not degenerate. There is no low dimensional subspace containing many of the points. So we can apply this change of bases, move them to be in an isotropic position. So why is this useful for us?
Shachar, perhaps just one comment about
Yes.
this. Yeah, I mean, these ideas, Barth is in Banach space theory.
Yes.
So these are very basic in convex analysis. The first thing that you know already, from school, you have a set, you perhaps want to move it so the center of gravity is in the origin.
Yes.
Then you want to apply a linear transformation to the space that it's fairly round.
Mm-hmm.
And this is what this captures.
So if you do linear transformation, yes, but then you don't get unit vector. If you want to renormalize, then it becomes slightly trickier, but yes.
Yeah, for linear transformation, that's very, very old.
Yes,
It's a
yes, yes.
basic technique in Banach
Yes.
space theory.
Yes, I agree. Okay, good. But okay, so what does this buy us? So let's say we could replace x and h with this sort of isotropic set of points and this new hyperplane. Then the point is that, if I set, and this is true in any direction, right? In any direction, I know that the L2 squared on average is like 1/d. So if I choose this direction to be this sort of a star h, so this new hyperplane that I got, then it can't have all of those be really, really close to 0. And the average still be 1/d. So at least some reasonable fraction of them have, large margin. And if you do the calculation, about 1/d fraction of the points could have large margin. So it could be that 1 over d have really large margin, the rest have margin close to 0, and there is no way of changing that. Okay. So at least we can get something out of it. So we move from basically all the points being close to the hyperplane to some fraction, like 1 over d fraction, being far from the hyperplane. So we can apply that. Just one quick thing. Why can we sort of play this game in our minds? Because we don't really have access to h. But we could still do that. We could say, well, what we really want to ask is questions with respect to a star of h. Like, what's the label of some point x that we're going to care about later with respect to a star h? Well, it's just the same as doing that. So we could pretend in our minds we have access to a star h, although we don't really have access to it, by applying this pre-linear transformation to our points. Anyway, that's just small, minor points. Okay, so let's see what can we get from this vector scaling. So we can guarantee that 1 over d fraction of the points have large margin. So we learn them using about d queries. And you do that, you need about d squared log n queries. So why d squared? Every time that you want to learn the high margin point, we pay about d queries to approximate the hyperplane. We can only guarantee this by just 1 over d fraction of the points. So you have to pay d squared. And this is where basically everything was stuck. Because everything that we did here, it doesn't matter if you use these sort of ideas or use ideas coming from geometry, all of them got stuck at d squared. So the technical question here is, why do we get stuck at d squared? And what I want to tell you about, which is really, this is where this new work starts, is saying, if you look at the more detailed structure of the points, you can get beyond d squared. Okay. But maybe before that, are there any questions up to now? So we had these two generic ideas. Points far from hyperplanes, we can learn by some simple approximation, and with this vector scaling trick that moves at least a 1 over d fraction of the points to be far from the hyperplane. But we cannot in general guarantee that you move more because there are counterexamples. Okay. So what can we do now? So now we want to look on the refined structure of our data. And this is really where the fun begins. So let's assume we have n points. And let's again, for the sake of the exercise, let's sort them by their margin. So x1 is going to be the one that's furthest away from the hyperplane, the next two is slightly closer, and xn is the closest one to the hyperplane. What do we know so far? And we can already assume they're in isotropic position because we can move them to this situation. So we know something about them. The first n over d fraction of them are far away. But the rest we don't know. And in general, they could be very, very close. So the idea is to say, well, let's just actually try to understand how does this margin decay. Does it decay slow or does it decay fast? So there could be two situations. One situation that's good for us, saying, well, not all that we know to guarantee this 1 over d fraction of the points being far, but maybe in our case, many of them are far. In this case, we're good. Like if half the points are far, then we pay d queries, we learn half the points, we're done, right? That's good for us. What's bad for us? What's bad for us is to say, well, maybe there's like this sharp, drop. Maybe up to some point, they're really close, and then there's this drop down, like this cliff, and now they're really, really, really close to the hyperplane. That's bad for us, right? So now what we're going to say is that maybe we can try to take advantage of that and learn faster. Okay? And notice we don't know, right? We cannot compute this because we know the points, but we don't know the hyperplane, right? So this is something that we just plain sort of in our minds, but we don't know which case we are in, so we sort of have to sort of figure that out along the way. So here's the first sort of structural lemma. It says, whatever points you give me with a hyperplane, you can always find k with the following guarantee. And I'll give you the quantitative bounds in a second. If I take the first, again, n over d is just sort of so the first n over d have large margin. And I'm saying the first k batches of n over d have large margin. Then you go up to 2k, guarantee you nothing, but from 2k and onwards, they have really, really low margin. So this said that for some k, no. So it's not look like that. So here we're at some k n over d, and here we're at 2k n over d. And there is also going to be such a k. Okay, now so I need to give you what do we mean by high and low. So actually I'm going to show the proof of this lemma. I just want to, again, so what do we have here before I show the proof? So if k is large, if k is a linear in D, then we're happy. Have the constant fraction of the points have large margin, we can win. Otherwise, we know of this sort of very sharp decay here, and then the question is how can we take advantage of it? Okay, so here's more quantitative dilemma, and the proof is simple. I'm going to prove the proof, here at the bottom of the slide. So fix capital D to be some large enough poly D for some later, like D to the 10 or something. Then there's always this K, such that there's some notice of what we will call large margin, which happen to be quasi-polynomial in D, and you see why. And all these points have large margin, and all the rest have low margin, and the high versus low is this sort of multiplicative gap. So up to here, you have margin M, and from here you have margin M over, D. So how can we prove that? We just sort of do pigeonholing. Okay. That's it. So that's it. So let's just set L to be N over D for simplicity. And think about the points, the Lth points, the 2L's, the 4L's, the 8L, the 16L, and so on. And they're going to decay. Well, there will be two cases. Either they decay slowly, so only by a factor of, let's say, capital D in each time. So at the very end, you decayed by D to the log D. Or at some point, you decay by a lot, and then you stop. Okay, so yeah, see. The proof is simple, but conceptually, that's interesting. So what I want to show you is how can we take advantage of that. Yes?
So for this lemma, could you have just rephrased it as have a sequence of numbers?
Yes. Yeah. Is it sequence of numbers? Yeah. We don't use geometry here at all, right? But we are going to use geometry to say, well, if K is small, we can sort of do something where we can save on the number of queries that we make. Otherwise, this is sort of, it is a structural result, but like a useless structural result. So it's sort of less interesting. Okay, so we have this lemma. So here's going to be the interesting geometric part. Let's assume we have this for K. What we know that these points, all of them have low margin. But we can prove the following thing. Because we know that the point is in isotropic position, there is a subspace whose dimension is linear in K, 10K, such that all the points orthogonal to it, the whole subspace, have low margin. Okay? So we move from just saying these points have low margin to saying a whole subspace of dimension D minus K has low margin. So now this is sort of one thing we can take advantage of from this sort of structure. So I'll give you some ideas about the proof of this lemma. So the key idea here is to say that the following thing. You can find a subspace where let's say all the unit vectors in it are not just spanned by these points, but they're effectively spanned. So effectively spanned means they're spanned, and you write a unit vector as a linear combination of them, and the linear combination with coefficients are not too big. So if the coefficients are not too big, and all of those have low margin, then all the other points are going to have low margin. Okay, so but a bit more detail. Okay. So here's again, I'm not giving you the full idea, but just a gist of the proof. So you can look on the covariance matrix of all the points that we know are going to have low margin. And you can take V perp, so the one that's going to be of low margin, this will be the span of all the large eigenvectors of this covariance matrix. And then you can prove two things. First of all, every point here, because the eigenvectors, I mean for like large eigenvalues, or not too small eigenvalues. Because the eigenvalues are not too tiny, you can prove that every vector there is effectively spanned by list of points. And because the list of points is in isotropic position, you can prove that almost all the eigenvalues are going to be large for this covariance matrix. Only very few of them, only order of k of them, are going to be very small. Okay. So again, this is, I won't show more details about the proof, but this is sort of something geometric we can take out of this type of sharp drop. So really what we know is that, again, pictorially, is that, if we have this set of points here, if this is our hyperplane, and we have like, points very, very close to it, and we have this number k, then really there's this sort of dimension k subspace that explains everything to us. So the points that are far are sort of spanned in this low dimensional subspace, and the ones that are sort of close are sort of, really are because they have like almost no projection to the subspace, and there's this big subspace where everything have, low margin. So how do we take advantage of that? So this is this lemma. So basically, what you can just project to this, if you knew this subspace, which we don't, but if you knew it, you can just project all my points to this subspace. And what you're going to get is that basically the margin is not going to change very much. Now the points might move a lot, but the margin is not going to change. And the reason is because high margin points are going to stay high margin points, and low margin points we know they're going to be small on this sort of on V-perp. So again, I'm sort of skipping technical details here, but by doing this type of projection, to this dimension projection, we can basically, at least a point that we have a hope of solving, the one with like reasonable margin, we can solve it in a much lower dimension. And basically know that we're not going to get any mistakes. So again, so here's basically where we stand so far. We know existentially, again with this number k that we know exists, we know there exists this subspace of dimension k that contains about nk over d fraction of the points. They have a large projection to it. Others have tiny projection, but we're not really trying to say anything about them. And we know that all the points in the orthogonal complement have really, really low margin, so projection to them doesn't really make a difference for margin. If we happen to know v, which we don't, and we happen to know k that we don't, then we can do the following idea. Let's just solve this high margin points problem, not on the whole space, but on this low dimensional space, has dimension k. We only need to make about k queries, and the fraction of points we learn will not be a constant fraction, but to be about k over d fraction of the points. But it's okay, we couple the number of queries we make with a fraction of points that we learn. So as long as we can find this subspace and find this k, we can keep this process until we learn many of the points. But of course, I told you nothing so far about how can we actually find this subspace, and how, because all of the proof to it exists using some linear algebra, or I told you there is a linear algebra proof for it. It doesn't tell you anything about how to find it efficiently. Yes.
Did you say that the space spanned by the...
Yeah, but I don't know the point. I don't know which points have large margin and small margin. I said, remember, I sorted them, right? I don't know this ordering. I don't know, right? No, this was just an existential proof. Okay, I can't really do it without actually knowing the points. Okay. So again, so this is where we stand so far. If we had a way of knowing this number k and this subspace v, we can project to k dimensional subspace, this v, query about k points, learn about k over the fraction of the points, repeat this process, and after you make about d queries, you're going to label about, let's say, half the points. And then this is what we'll try to do. So the last thing we have to do is somehow find a way of finding this k and this v efficiently, using just linear queries. So before I'll show you that, any other questions so far? All right. So how do we do that? So how do we find structure? Not just move knowing this structure exists, actually find it efficiently.
So, Shachar,
Yes.
just to make sure. So we don't care what the value of k is because the bang per buck is the same.
Yeah, exactly, it's a bang for buck, yeah. So k will be something, I can't guarantee anything, but if k is small, I'm going to make a few queries and learn a little bit. If k is large, I make many queries and learn a lot, but they're coupled to each other. Yes. So what's our setup so far? So we have this set of points that, again, in our minds are sorted by margin. We're trying to find two things. K, which is a number where the margin of this xk over d is much more than the margin of the points of twice as much. And then somehow the effective span of all these low margin points. And in order to do this efficiently, it actually helps to go through some new query model. So I'm going to call this an approximate max query. So it's going to be a new type of query. First, I'll show you what it is, show you why it's useful, then how can you simulate it using standard queries. So what's an approximate max query? I give you a set of points, capital A, and I ask you to find me the point that has about the maximum margin in this set of points, right? So find maybe the exact maximum. I need to query all the points in A and find the maximum, but I don't care about the exact. I want approximately the maximum, okay? We're going to call this an approximate max query, okay? So assume for now that we had this sort of more powerful oracle that could actually ask them these approx max queries. So let me show you first how using these approxmax queries, you can actually solve this finding K and V. And then I'll show you how we can simulate approxmax using standard queries. So let's see, what do we do with it? So let's first show you how do I recover K. So that's going to be relatively easy. Okay, 1 second. Okay, so what do we have? So first, I'm going to sample a set A1 of size about D, okay, of random points. And then I'm going to have the following process. Every time I'm going to compute xi, which is going to be approximately the maximum value of AI, the point with the maximal margin, I'm going to remove it from a set of points. I'm going to sort the points method over margin. When I actually compute the margin for these points, I'll sort them. And then I see among the points I know so far, these k points, or whatever I points, either a sharp drop. If there's a sharp drop, I stop. Otherwise, I keep going. And you can show that, if you choose, because we really wanted a sharp drop, and you choose this drop to be, slightly less of a sharp drop, then this is going to work. Basically because it's going to be a random set of points, so with high probability it's a good approximation of the global structure of the space. And again, this again uses the fact that we're in isotropic position, to no outliers lie somewhere in some weird directions. So in particular, if this sharp drop happens after about k n over d, then I need to sample about k points to discover this sharp drop. Again, at a high level. And finding space V is going to be sort of similar, but slightly more technical. I'll go quickly through it. So basically, again, you choose something. So first you say, I'm going to sample a set of size about D. I'm going to take its approximate max, and I'm going to say, well, let's assume this point has some reasonable margin. I know that about 1 over this fraction of the points have large margin. I sample, D points. One of them should contain large margin. I find something that's approximately large, so it's good enough. So A, we know this set A has large margin. That's going to be a reference point. And then what we're trying to do is basically sample many of these points, of the low margin points. Now, assume K is small. Well, it's almost all the points. So if I want to approximate them, I want to approximate about D points. But I don't want to make D queries. I want to make K queries. So what do? I'm going to say, well, sample a set of size about D over K. There is about constant probability all that's going to be contained here in this set of low margin points. How do I check for it? I'm going to take the point in this set that has the largest margin, and I'm going to make sure this is still going to be really less than the margin of my reference point. If it's really less, then I know that all the points in my set have really small margin. So with one query, I verified the margin of about D over K points. So, and this is like a rejection sampling. So I do it about K times and you're done. Okay. So this approximate max is useful, but of course we don't have access to this approximate max. So the question is, can we simulate approximate max query by just standard linear queries? Okay. So here's a lemma. It says, let's have a set A. Doesn't matter, it could be poly D, doesn't matter. I can simulate approximate max query in A, not by standard query, but by randomized query. I can find randomized queries that with high probability are going to give me a point in A that has about the maximal margin. And in the number of queries, it's just about log A. We're going to do sort of a binary search using randomness, and you'll see why in a second. I just want to point out that if I didn't want approximate, I want exact max, I need A queries. So by allowing this approximation and allowing for randomness, we can save exponentially in the number of queries. So what's a trick? So here's a trick. I'm going to take a set of points, and I'm going to partition it into two halves. The first half, the second half of about the same size. And I'm just going to take a random Gaussian combination of the first set of points. So if I have a set of points, let me do it this way. If A is a set of points, let's say RD, and I look on the sum of AI, GI, where GI are all standard Gaussians. And let's call this new point, I don't know, A star. Then I'm claiming that the margin of A star is about the maximum margin of AI. Why? let's take the point here with the largest margin. Then, because we're choosing random Gaussian combinations, it's not likely to get cancelled by other points of large margin. So points of low margin are not going to cancel it. Other points of high margin are going to go in different unrelated directions. They're unlikely to give me really, really strong cancellation. So there's going to be some tiny probability that this is going to be small margin, but otherwise it's going to be close to the maximum.
Isn't this the same idea of heavy heater sketching?
Yeah, it's not something new, but we just use it here for a different purpose. Yeah, I mean, the proof is not hard. I'm saying, yeah. So just sort of, there's not going to be any weird cancellations with high probability. So you choose either A1 or A2, the half with the largest margin that you got, just keep doing, recursively. Okay, so we can approx max margin by, again, all the sets we're going to care about are going to have size poly d. So all these approximations are going to give us log d, and they're going to be a probability of error, which is going to be about 1 over poly d also. So there's going to be some small probability that you have to deal with, that you make a mistake in this randomness, and the Gaussians are bad and we're screwed. But otherwise, we know we're going to get a good estimate. Okay. So what do we stand so far? Let's try to put everything together and see what do we have and what sort of breaks down. So again, this is a setup, but so we have endpoints in RD, an unknown hyperplane. Here's a general algorithm. We move to an approximate isotropic position. We find this structure K and V using these approx max queries. But we actually don't run them, so we run this randomized query that's going to give me the right answer with high probability. And then we use dimension reduction to V to learn using about K queries, and then just keep going. Okay? So where could things break down here? Well, it can only break down if somehow I failed to simulate these approximate max queries with my random linear queries. So this is what we can say about this. Is again, ignoring all the details and just about the black box. This is what we can say about the algorithm so far. It's a randomized algorithm, so it makes randomized linear queries. It's a randomized linear decision tree. It makes about D linear queries. With very high probability, say 99%, we're going to label almost all the points. Let's say we stop after we label 99% of the points. Okay? So we're going to label them correctly, because the error probability is going to be small enough. But with like 1%, my approximate max simulation fails. I have no guarantees. I get some adversarial answer. I know nothing about it. Okay? So again, and so for now, let's just sort of ignore everything that we know about the details of the algorithm and just think about this type of a promise. I give you this black box, right? That given you the arbitrary endpoints, runs about D queries, labels 99% of them, and you know, like with 99%, it's a correct labeling, and 1% you get complete junk with no assumptions. So we want to take this algorithm and make it into an algorithm that works. So first of all, labels all the points. So I want to make this into 100% and makes no mistakes. So I want to make this to be 100%. Okay. So we do it in 2 steps. So the first step is something called boosting. So boosting is this general technique in machine learning. It says, I give you a weak learner, something that can give you some information about your learning problem, and you can boost it to give you a lot of information about your learning problem. And if you apply these techniques here, what you get is the following step or progress. So we can view our current algorithm as a weak learner with the following guarantees, and applying boosting to it, or actually some variant of boosting, but something boosting-like to it, what you get is what we think about as a strong learner. So it makes now not D, but about D log n queries, because we could try to label all the points. With 99%, I label all the points correctly. And with 1%, you return arbitrary junk. So now all that remains is how to verify that I'm not in this junk situation, right? So this seems like this should be a much, much easier product. I give you this black box that can label all your points, and only with 1% returns junk. And you just want to verify it. Okay? So how do we do that? Okay, so this is what we had so far with the strong learner. Just to remind you, now the last piece of the puzzle is we want to replace this 99% with 100%. We want to verify that we're not making mistakes. So again, you can think about it as the following problem. I give you a set of points, and I give you a labeling to it. And you just need to make sure this labeling is correct. Okay? So how hard can this be? So you want to verify the solution.
So correct, you don't give me the H.
No, you don't get H.
You just want to see that there exists an H?
Yes.
Or
No, there is an H. Okay. So what you get these points. All right, so I give you here's a point, here's a point, sorry. Here's a point to the plus, here's a point to the plus, here's a point to the minus. And there is also an H here that you don't know. And H might agree with this labeling or maybe not. And you can query H. You can query your point, you can query other points. And you want to verify this labeling. Right? But of course you don't want to query all the points. That's n. You want to query what d or d log n. Something small. So we reduce this problem.
Why shouldn't you verify it only on the d log n points that you... So far you spent d log n queries.
I spend d log n queries, yes.
So in the verification...
But somehow for them we need actually more things. Yeah. So I'll tell you the answer in a second. It's a very good question. Why can't I just verify something related to...
You just want to see if you got junk or not, right?
Yes.
From the d log
Yes,
n.
yes, yes.
So to try to vary
Yeah.
besides this,
Adversarial check.
Yeah, so the problem is once
oh,
you make a mistake, you get an adversarial junk. And you want to differentiate the two. So what we do, again, is something I don't like. So we don't have a general solution for this. We don't have like a black box solution. What we have like a white box solution. We can go inside our algorithm, find all the places where we make guesses, verify them. Turn out to do that is actually much more complicated than it seems because the algorithm runs in steps and it's adaptive. So you have to do this adaptive also. It becomes very messy, very, very, very complicated and very
but it's
suboptimal.
not general,
And it's not general purpose. So I don't like this solution. I mean, it works, it gives us something, but I don't think it's the right solution. So I won't tell you anything about it except that it's not the right solution. And one way you know it's not the right solution is because you get this horrible bound out of it, right? You should never get this bound from the right solution.
So, by the way, this is strictly an easier problem
Yes.
than the original
Yes.
one. Now you're not only given, you don't only need to label all the points, but really you get the label, just you need to verify
Yes.
that it works according to
Yeah,
the
and also you get for free a black box algorithm that can label any point that you want, and it's going to be correct with 99%, and makes almost the optimal number of queries. So you can use this black box, and you work with this easier problem.
Or if I just want to verify the labels without the black box, it's still going to be omega n, right?
Yeah,
So the third example-
naively, yes. Naively, yes.
No, I mean, suppose that I'm not allowed to use to query just for this verification.
Oh, yeah.
I'm not allowed to.
Yeah,
query
then again in
on
the end.
points.
Yeah,
I'm still back to the end.
yes, exactly.
I see. So I need to use your
Also-
algorithm
yeah.
basically.
Or maybe not, you don't have to, right? But it is
But-
strictly an easier problem, right?
Okay.
I mean, you don't have to, but the only way we know how to do it is basically to say, you verify it, you create new problems, you run on them, you create new problems, you run on them, you create this sort of horrible, recursive algorithm that you balance the parameters and you get this horrible bound out of it. Anyway, that should not be the right solution. It should be a cleaner solution. So basically, very, very high level, here's the main algorithm. So we define this weak learner that learns the most points with small error. We use boosting to learn all the points with small error, and we use this verification, this random type of like self-reduction to verify the solution. And what we get in our number of queries has two parts. These parts come from like the first two things without the verification. And this is almost optimal up to this log square d, and the algorithm is also, I mean, it has details, but it's, I don't know, I think it's structurally nice. And this part is like messy and like, complicated and not the right solution, I think. How to verify the solution. Okay. So this is just to summarize. This is what we showed. And again, I just want to tell you, but again, repeat this question because I think it's a very clean question, and I think people could come up with like, different ideas on how to solve it. I mean, I think, I'm hoping somebody will come up with like, a nice, clean solution for it. So again, let me repeat the question. You get for free the following black box, an algorithm that you give it whatever endpoints, it labels all the points with essentially the optimal number of queries. With 99%, you label all the points correctly. 1% you get junk. You just want to verify you don't get junk. And yeah, you want to do it, ideally in some black box way that doesn't quite know what this algorithm here is doing, which we have no clue how to do.
Question.
Yes.
So these probabilities in line 2 and 3 are
Yes, but this is not a distribution. This is not a probability over the points. For every set of n points, you get so you run this algorithm twice. They're independent. This is about the internal randomness of the algorithm.
I guess to some degree it sounds like the original problem, because you're only thinking about the situation where you got an arbitrary labeling, right? So then
No, because if it's arbitrary labeling, maybe it becomes easy to verify that it's very far from the correct labeling. So the hard case, the labeling is almost the right labeling, but not quite. But then you know the labeling, so now you don't need to. The labeling doesn't cost you queries. Like that you can do whatever pre-processing you want on the labeling. Find maybe a set of potential candidates for a hyperplane and verify it. You do whatever you want. Like you don't pay for computational time. You just pay for queries. So maybe you can do a set of pre-processing to the labeling. I mean, first of all, if the labeling, for example, doesn't come from a linear separator, then you can just reject it to make it 0 queries. Right?
I guess what I was thinking is that this problem sounds a little like someone just gives you like a random labeling, and then you have to figure out if it's right.
No, I think random would be easy because the random will not come. Remember, you have n points, you have 2 to the n labeled in total, and only about n to the d that comes from like a geometric labeling. So if it's random, then it will most likely not come from this geometric labeling. So you can reject it to make it 0 queries. So the random labeling problem is easy. Okay. I have one more question, which is, so far, this was a combinatorial question, so we cared about queries, but of course, if you want to actually translate any of that into something that people might use in practice, then you want to say, well, we shouldn't use this crazy, Gaussian random combination and vector scaling that gives us crazy queries. You want to use simple queries. Okay. So in the previous work, we were able to solve some problems like that using simple queries. I'll tell you what these simple queries are. So I'm going to have this of points. So x1 up to xn are my points. I have h, which is my hyperplane. So we said we had like a label query, which is labeled just h, xi, and we can also do what's called a comparison query, which is h, xi minus xj. Okay, so you're allowed to either ask about one of your original points, or you can compare 2 of your points and say which one has a larger margin. Well, it turns out that if you just use this type of queries, using completely different machinery, you can show that in the plane, you can solve this problem in order log n. And also in high dimensions, you can solve it if your points are not pathological. So, for example, if they have bounded bit complexity or large margin, then you can use these types of queries to solve the problem, with essentially the optimal query complexity. But we know that these comparison queries fail in pathological cases.
So, yeah. Can you say a bit more what pathological means?
Yes. So, for example, pathological would mean something like, maybe if h, xi scales like, 2 to the minus I. So some are big, some are small, they decay exponentially fast. That's like a pathological case.
No, but in the paper, what are you assuming? You're not assuming that. How do you?
Okay, you're asking in the so pathological. Okay, what is non-pathological?
Yeah.
So non-pathological will be one of the following 3 cases. So one is in 2 dimensions. You don't need to assume anything. Or you could assume that all the xi's are, let's say, for example, in 0 up to some b to the d, where b is small. So they have maybe up to scale in their integers. Or 3, you could assume that h, xi is at least gamma for all I. So either 1 or 2 or 3. But we also know that if you don't do these assumptions, you can build pathological examples. Okay, so somehow to many practical things, imagine you're trying to do some actual labeling problem. It seems reasonable you ask people, here are 2 things, maybe you're trying to decide if an X-ray is of a patient who's sick or healthy. You can ask a doctor, is this sick or healthy? But you can ask here 2 X-rays, which one looks more healthy or more sick, right? So that seems reasonable. But the problem is that if you move to even R3, we don't know what to be the analog of simple queries. So here's what I would like to do. I would want some notion of simple queries, maybe not comparison, maybe something slightly more general, I don't know, which would also work in R3. But we know that this specific one fails. So we can build, even in R3, we can build pathological counterexamples. But I'm suspecting there should be some notion of simplicity that should work in every fixed dimension. But we don't even know what the right question to ask here is. Like, what should be even the right definition of simple? Yes?
So why is condition 3 not
No, so what I want to say, so here's the goal. A goal is to get to be work with some slightly more complex notion of comparisons, some three-ways comparisons. I want to get into R3 and make 0 assumptions about the points. You should look for any set of points in R3 by generalizing comparison to some type of three-wise comparisons. But again, I don't have a suggestion, because these are ones I know of don't work. Sparse would work. If you do sparse, at least the ways you know how to do it, you're going to lose something. Yeah, but let's say if I allow you xi minus some arbitrary coefficients here, like, you can choose something like, irrational number, and based on the things change. I mean, you want something that sort of has like small, like ideally it's sparse with like small integer coefficients. That would be nice. But I think this fails. The counterexample also failed for that. So you need something different. Anyways, the simple suggestions don't work, and probably so. So you need to come with a good suggestion what would be a three-wise comparison. Okay, and I guess the last thing is just de-randomization. So in all this part about this non-pathological case, we could de-randomize our algorithms. I mean, not uniformly, but sort of non-uniformly, using some type of compactness type of arguments. Here, because this is an adaptive algorithm, even the compactness arguments fail. So we don't have a generic compactness type argument that de-randomizes this type of adaptive linear decision tree. So that's, again, maybe a more abstract open question.
You only need to full half spaces in your algorithm for which pseudo-random generator exists.
Yeah, but you want to work for pathological points, so the margin could be extremely tiny, so you can't really allow errors. Yeah, once you allow errors, everything is easy. This is like the margin case, right? Once you allow margin, we know how to do this in a much better way. So this is really about the combinatorial question where you don't care about applications, and the margin could be tiny, 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 but you still want to be correct. It's a different game. Okay, thank you.
More questions to Shachar?
Yeah, so how similar or different is this than the Ezra? Sharir?
Very different. So the Ezra Sharir one, which is also similar to the previous ones, is always based on some type of geometric decomposition.
Yeah.
And this doesn't look like geometric decomposition. This is sort of more taking this sort of sample points, and then we do projections, and we do boosting, so it looks very different. I think that it's interesting, how does that look if you dualize it?
Yeah.
I don't know. It looks very different, and it's unclear how it looks like. But somehow it doesn't look like partitions.
So the whole, I mean, there is a very rich industry of partitions. It's a
I know.
different group.
Yeah.
So you cannot somehow import any of these ideas to.
So all the partition ideas seem to get stuck at this squared. Yes.
Lower bound on a box max deterministically, or you said it exact max.
Lower bound on approx mass deterministically.
The number of queries.
Yeah, because think about it. Let's say I give you d points. I tell you one of them has margin 1, the rest has margin 0. But you don't know which one. So that again depends. Or you can, I think whatever deterministic thing you're going to do, you can always find a configuration that's going to fool it, right? Using sort of linear algebra. So you need somehow randomness there. As far as I could tell.
More questions?
For this last question you asked,
Yeah.
when you say what type of comparisons you allow me, what do you allow me, taking determinants?
Okay, so what you're allowed to do is to do the following thing. So what did we do here? So we said we started from 2 points, let's say x and y. We created a new point x minus y, and you're allowed to query x minus y. Right? Now I tell you, you need to take 3 points, x, y, and z, and you create a new point, I don't know, w. You don't have to do it in a linear way. In fact, I think at some point we prove that linear is not going to work. So this might be something nonlinear in x, y, and z, but it's going to give you some information. And you can do also those, but you need to add something else here. Seems to be. That's what Mickey was saying. Yeah, if you're allowed to put here arbitrary coefficients, then you can do other tricks, but then I wouldn't call it simple. I want simple bit. I want bounded bit complexity. So yeah.
By the way, how long does it take to find this transformation that moves set?
Oh, that's good. So I think the original proofs, I think it was by Avi, right? And I forget who else. They did it for different purposes, and then people keep improving. I think now Daniel Kane has a paper where he can do it in polynomial time.
Oh, you mean polynomial?
Yeah, so I think it kept improving, and I think Daniel now can do it in polynomial time. So this transformation actually has many applications, not just for this specific problem.
This you refer to Twig's Wiggington that you mentioned? Or?
No, something from the 90s.
So Shachar, it's
I think it was he had this proof where he was using the permanent to understand something about this. I think his algorithm ran like an exponential time or n factorial time or something like that. And then there was and I think there was some connections to this sort of non-commutative operator that he's doing now. And I think something gets connected to many other things.
so it's not like a STP or something?
No, I don't know. I think it's a new paper yet. I haven't read it yet. That Daniel has.
Didn't someone here said it was known from the 70s? Like
No, for linear transformation and not from the 70s, much before.
But that's what.
No, because you rescale.
Oh.
The rescaling is non-linear. But because you rescale, you get actually much more power because now everything is unit vector. So, people have been using these things, I know, like in study of locally correctable codes, it's been used, and actually this operator business has been used, and like in a bunch of other places. So it's like a very general, approach to massage whatever points you get into looking nice.
Anyway, there was a very famous at the time, was a big thing, Bourgain-Milman, where you are able to keep the norm of both in the primal and the dual, you could get them to be, the body is very nice. Perhaps
Yeah.
it was, terrible paper to understand, but the results, it's something that's perhaps worth.
It's interesting, yeah.
Yeah.
So what's the result there?
More or less what I said, what I more or less remember. No, if I look it up and
Okay,
I'll explain it to you. The results are easy. The results are easy
Yeah.
to state. The proofs are
okay,
easy.
yeah.
Stay in
Hi.
Shachar.
Thank you.
So, see you, Erdős lecture in 2023.
שווה לך לבדוק את זה.
מילמן, אני אסתכל על זה.
אז הייתי יותר קרוב לעסקי הבית, הייתי שומע את זה. וזה היה ממש מהפסגות של התחום שלנו. שווה להסתכל. להסתכל עכשיו, אם אתה רוצה אני אשמע.